the worksheet from today's solutions practice, right? This is the first worksheet. So this is the one with the acid-base concentration and molarity one. We're going to go through that one first. If we have enough time, then we'll do some of the advanced one afterwards. And so if you haven't pulled this up, then I definitely would recommend doing it. Right now, we're just filling in our definitions. And so with Dimitri's help, we filled in molality here. And so now we're looking for one of these other three. So who has another definition for one of these other three? If we know molality is moles of solute per kilogram of solvent, what would our next one be? If you don't want to tell everyone, you can just message me individually, or you can just put it up in the chat. That is totally fine. You can also unmute yourself.
Wouldn't mole percent be amount of solute in mole over total of solute and solvent in mole?
Very good. Yeah, so it's going to be our moles of our solute. And then the difference is this is going to be the total moles. And we can call that solution. But you're right, that is also the moles of the solute plus the moles of the solvent. The only difference is because it's the fraction, then we don't have to multiply it by 100%. If it was mole percent, then we would take that and multiply it by 100.
Oh, okay, makes sense.
So Jeremiah, you're saying molarity is moles per liter, and that's moles of what per liter of what? In the same way that a molality wasn't just moles per kilogram, right? So it's going to be moles of solute, and then this should be liters of the entire solution. Yeah, right? So we have to remember that our solution is going to be both the solvent and the solute. Very good. Who has mass percent? Our last one here. Right? And you're saying that that's mass divided by total mass times 100%. But what should that mass on the top be referring to?
Moles.
So if we have mass, then it's not going to be moles, right? Those two are two different things, right? Mass is the amount of material. Moles is the amount of material once we take into account its molar mass.
Oh, it's mass percent, never mind.
Right? It should be the mass of the solute. Very good. So it's whatever we're interested in. So if we wanted to, we could refer to all of these as solvents, right? If we wanted to look for the side of things. But you can kind of imagine that whatever we're interested in is going to be that top part. That's the concentration we're looking for. So in a lot of terms, or a lot of times, we're looking for the solute, right? Because that's what we've dissolved in there. And so we can kind of look at this next one down here with this malic acid. And we were going to turn it into a solution. And so then we're going to go ahead and calculate all four of those things for that malic acid. Right. Now, in here, I should have added one more clarification to help you out. And that's going to be that you can assume that the volume of the solution is equal to that of the water. Now, when we really make solutions, the volume can sometimes change as we start to dissolve things inside. Sometimes your solution will increase in its volume as we start to put more material inside because the water solvent particles will start to space themselves out. Sometimes when we mix them together, the volume will actually go down. And so it just kind of depends. And so we're going to put this addition in here, this assumption, so that way we can go back and forth between the molarities and our volumes a little bit as we're looking at that, because we know that water, what's the density of water? One, and what's the units?
Gram per liter.
Gram per milliliter, but very good. right? So the density of water is 1. And so that's how we can kind of use that 500 grams to move us back and forth. So we're going to start with this problem, right? This 2.56 grams of malic acid, and we're going to try to go from there. So what would be a good one for us to start with? Which one of these 4 concentration units would you guys like to tackle first? It's given us the grams of the solute and it's given us the grams of the solvent. So we could start with molarity. And to do our molarity, we would need to find the moles of the malic acid. I'm going to use the chemical formula there. So C4H6O5. And then we have to find the volume of the entire solution. And so there's a little bit of preparation that we need to do for that. Right? We have to find volumes. We have to find our moles. Is there another one that requires less math for us to start out with?
Sorry, what was the question?
We're trying to figure out from these 4 which one we should start with. And while we can start with molarity, there is an even easier one that we can start with first that doesn't require as much preparation as us finding moles and us finding the volume.
The mass percent?
The mass percent is a good one to start with. And that's because our units are already in our grams here, right? We have 2.56 grams, we have 500 grams. So I want you to go ahead and let's find our mass percent. And so remember that we have that up here. It's the mass of the solute divided by your total mass. So I'm going to give you guys a moment to put that together. And when you have your answer, go ahead and put that up in the chat.
So the total mass is going to be the mass of the solvent plus the mass of the solute, right?
Very good, right? So we have the mass of the solute and we have the mass of the solvent. So the mass of our solution should be both of those things put together, 2.56 plus 500. And so that's going to be our bottom number. Right? So our mass is given, right? We know the 2 pieces of our solution, so we should be able to figure out their total mass. So that becomes our 502.56 grams down here. And then what number goes on top?
2.56.
2.56. And so what percentage do you guys come out with?
50.94.
50.94 seems a little bit too high.
0.5.
Oh.
0.5.
Oh, okay, got it.
I think you did it twice. All right, so this is going to be our mass percent. And so how we got this bottom one, this 502.56, right, is that if we have a solution, that solution is going to be made up of 2 things. It's going to be made up of what we dissolved in there, the solute, and we're going to be made up of the other part that's doing the dissolving, the solvent. So the total mass of that solution is going to be equal to those 2 parts. In the same way that if you have a container and you put 10 grams of rice inside, and then you put 10 grams of pasta inside, your total container is just going to weigh 20 grams because you would add those 2 things together. That's the same thing that we do with our solutions. We just added in the 500 grams of the solvent, which is our water, and the 2.56 of our solute. Very good, Dimitri, just like that. Right? So that's one of them down. We have our mass percent. And so now we can start moving into some of these other ones. And so we can go and we can try to do our molarity now. Now, how are we going to get this top part, moles of C4H5 or H6O5? How can we take our 2.56 grams and find out the moles?
Molar mass.
The molar mass, very good. So our molar mass, I'm going to get a different color for this. So for C4H6O5, what's its molar mass?
$134.0874.
134.0874 grams per mole. And so if we take our grams, 2.56, 1 mole, 134.0874 grams, we can find our number of moles. Oh, sorry about that. Now, I like to keep this separate for now because we use moles of C4H6 or O5 a lot of different times in this problem. So now instead of having to recalculate it every single time, I can just use that value. All right. So we have our moles and we can plug that into here. How are we going to find the volume of our solution?
I said in half liter of water, 500
Huh?
grams.
Very good. It's saying that we have half a liter of water. And I gave you that assumption that we could assume that the volume of the solution was equal to that of the water. Right? So that means that we can go ahead and we can plug into here a half liter of water. And so that should be 0.500 liters. And we can use that to get into our molarity. And so what value do you guys get for your molarity?
0.0382.
0.0382. And if we want to use the symbol for molarity, it's going to be that capital M. Now, because we have molarity and we have molality, be careful about your M's. Make sure that you make your molarity one capital because your molality is going to be a little case or a lowercase. So you just want to be careful with that part. So let's tackle molality next. How are we going to do molality?
The same, but convert the gram to kilogram.
So this time when we do our little m, we're going to take that 0.01909 moles, and we're going to take the 500 grams, and we're going to turn it into kilograms. So how do we turn grams into kilograms?
10 to the negative 3.
10 to the negative 3. We divide it by 1,000. And that's how we can get a molality. So what is our molality for this?
It's going to be the same, right? As
This one's going to end up being the same as our molarity, which is not always the case. It just happens to be that way with water because water has that density of 1 gram is 1 milliliter. And so as long as our solution, its total volume is the same as the volume of water, then its molarity and its molality will be the same. But if we use a different solvent, they don't always match up. Right? So it's just a special case with water. So now are we done, or is there one more that we need to figure out?
Mole fraction.
Mole fraction. Yeah. So I've run out of space here. I'm going to consolidate this down a little bit. So that way we can work on our mole fraction. And so for our mole fraction, what do we need to do? If we want our X, right, that should be the moles of our C4H6O5. And then what's going on the bottom?
The total moles.
Our total moles. So we know how many moles of the solute we have.
Mm-hmm.
How do we find our total moles? What else do we need?
Is it going to be the 500 gram divided by the molar mass of water?
Very good. Because right now our solution is made up of only two things. It's made up of the malic acid and it's made up of water. So in the same way that we could figure out the mass of the solution by adding them together, like what we did down here, we can also do that with our moles. We just need to take that 500 grams and we need to turn that into moles. So if we take 500 grams of water, and we divide it by its molar mass, we can figure out that there are, oh, I didn't do this math yet. Let me do, how many grams of, or how many moles of water there? So 27.75 moles of water. Now, do we need to divide that by, or do we need to multiply that by 100? Or do we just need to report it as the decimal?
Report it as decimal.
Report it as the decimal. And so what value do you guys get for your mole fraction?
Zero 0.000687.
Very good. I actually have it as 0.688, right? When we get down there, so it's 6.88 times 10 to the minus 4. Right? Both of those would be fine. And so that's how you can go back and forth between your concentration units. Did anyone have any questions on that part?
No.
So just pay attention to what it's asking for, right? When it asks for something in a percent, then it means multiply it by the 100% at the end. If it's asking for as a fraction, then you just need to compare their ratios, right? So that's how we get our mole fraction versus our mass percent. The other parts is you want to make sure whether the bottom is solution or whether it's solvent, because those two things are your other variations that you can kind of see between them. This is the same thing as what you do in this part of the worksheet. And so I'm going to let you guys work on that one by yourself. There's an answer key up so you guys can check your answers when you get to the end. But what you're going to do is you're going to take your different amounts and kind of move them through, changing from molality to mass percent to mole fraction, similar to what we kind of did up here. As an example, right, for NaI, we know that the 0.15 molarity is telling us that we have 0.15 moles of NaI versus how much water? One what?
Kilogram. Molarity.
1 kilogram of water. So if we want to get into a mass percent, then we just need to change this NaI into our mass. And then we can add that to our bottom and we would have the mass of the solution. So this is kind of how you can move back and forth between them. If we wanted it as a mole fraction, then we could take the kilograms, turn it into moles, and then compare it that way. So a lot of concentration units are interchangeable. You just have to know how to use your conversion factors to get from one to the other. This is a little bit more common about how you see solution problems, is kind of using them to solve for different concentrations. We saw this with our titrations that we did earlier this semester. We see them with how you predict like precipitation reactions and all of that as well. And so there's a lot that kind of goes into this one. So we're going to do a couple of these to kind of practice. So on this first one, we're going to take 6.73 grams of sodium carbonate, and we're going to dissolve it in enough water to make 250 milliliters of solution. And so it wants us to know the molarity of it. So go ahead and start with that problem. If you're not sure where to begin, look at the question and what it's asking for and start with what the units are for that. So if we're looking for molarity, then we know that this should be moles of Na2CO3 over the volume of our solution. And then separate those two parts. Since we know that we're looking for moles of Na2CO3, then how could we get there from our grams, right? So use that as you kind of piece those together. So I'm going to give you a little bit of time so you guys can practice that part. If you find your answer, your molarity, you can put that into the chat. If you have questions or you're stuck, you can also ask on that part as well. But I'm going to give you a couple minutes so that way you guys can kind of work through that and we can start to compare. Very good, Nita. So why would you think that it's 0? I'm going to give you guys another minute. Let's see if anyone can verify our different answers. Let's see how we did. Right. So that's a good question. So when you're looking at your molar mass, right, for our molar mass, you should make sure that you're including 2 sodiums, 1 carbon, and 3 oxygens. Right? So when we're looking down at your molar mass, right, you're off by, what is that? By 23. So it looks like you're missing a sodium in there. So it looks like the 0.254, we're getting some other responses in that support that. So that's good. And that is what our answer should be, right? And so we should take our moles and use our molar mass to get into our, or sorry, take our grams and use our molar mass to get into moles. And then once we have that, we just need to divide it by the liters of our solution, right? So make sure that you change that over to 0.250 liters. You then just use the 250. And then we have our molarity right there. So very good. Does anyone have any questions on that part? Is there any part you guys want me to clarify a little bit? Or are we ready to move on to number 2? It's okay, it's not a rush, right? So when you guys are ready, let's move on to number 2. And so we can think about that solution that we're going to make and think about how many grams of KMnO4. Right? So we can think about how many grams of KMnO4 we're going to use for that part. I'm going to scroll this up a little bit. And so our new solution is going to be 250 milliliters. We know the concentration of it. So we want to know how much we're going to dissolve in there. So if you want to imagine this, if you had a container with 250 milliliters of this solution in there, what we're trying to find out is how much of this KMnO4 should we have put inside for it to dissolve. And then they want that specifically in grams. So in a lot of ways, solution chemistry is kind of like our stoichiometry. We have to make those dimensional analysis charts. And so we're starting from a volume, milliliters, and we're going to try to end up in grams. So from our volume, we can use this concentration to help us do that conversion. We can change our volume into liters. So that way we can find the number of moles of our KMnO4 in the liters of solution. And then once we have that, how do we go from moles to grams?
Molar mass.
Molar mass. I figure if I ask it enough times, then we'll always remember. So that's kind of our pathway, right? Is we can use that concentration to help us, like a conversion factor, to move in between one thing to the other. So now we just kind of need to update our values in this. And so when you guys have your grams of KMnO4, you can go ahead and put that into your into the chat, and let's see if we can get those verified. So moles solute over kilograms of solvent is our molality, right? And so that would be if this M here, let me, was a small m. But because it's not, because it is a big M, then we know that that should be molarity, which is moles per liter. So we started off with our volume over here, right? So this is our volume of our solution. We changed that over to our liters. And then we use that to find the moles of our KMnO4, right? So what we did was we basically took our volume of our solution here and we multiplied it by this concentration. Because when we do that, our liters are going to cancel and we're going to be left over with our moles of our KMnO4. That next part is then we use the molar mass, which should be 158.03 grams per mole. And you guys are right that once you put that in, we should get out 0.494 grams because we end up with 0.4938 and we end up rounding up, right? And so that's kind of how we go through that part. So we're going to use the conversion or the concentration kind of as a conversion factor to move us from one to the other. So we can try the next one as well. In this case, we want to think about what we're starting with. So we know that we want 25 grams of this sodium hydroxide. What we're looking for is our volume in milliliters. So we're looking for milliliters on one side, we're starting with grams on the other. And so we want to start to put that process together. So from the grams of the sodium hydroxide, we're going to move into moles of the sodium hydroxide. Because once we're in moles, then we can use our molarity to turn that into a volume. Because now our volume will be on top, so 1 liter of solution. Now, how many moles of sodium hydroxide do I need for 1 liter of solution?
0.123.
0.123. So your concentrations are kind of like conversion factors. And then if we want to get that into milliliters, we just need to multiply it by 1,000. So go ahead and now update this chart with your values. So we can put in our 25.0 grams. We can put in our molar mass for sodium hydroxide. And we can move on for the rest of that problem as well. Once you find your volume, you can put that into your chat and we can see how we do. Armand, do you understand number 2 now? Or do you want me to go through that again? Good. So molar mass is 39.97. Yep. Now make sure you pay attention to the units that's asking for. Very good. And so just watch your significant figures, right? We should only end up with 3 significant figures. And so it looks like we're falling into that right grouping of answers, right? So with our 3 significant figures, we should get something like 5,080 milliliters. Or if you want to do that in scientific notation, it would be 5.08 times 10 to the 3 milliliters. So when we're using our significant figures, it's not that we can't be in the like 5,000, right? It just means that we have to make sure that we're only going out so far. Does anyone have any questions on that? Otherwise, it looks like you guys are pretty much on track for that. So from here, our next type of problems are things that we call dilution problems. Yeah. Now, a lot of dilution problems can get solved with an equation that looks like this. M1V1 is equal to M2V2. And what's going on in this equation is that if we take our molarity and we multiply it by a volume, we're really finding the moles of the solute. And for our dilution problems, the moles of solute in solution 1 is equal to the moles of solute in solution 2. So if we read through this question, they're saying that we are taking that solution and we're just adding in pure water. So the amount of the copper sulfate in it doesn't really change. The only difference is the volume of space that the solution occupies has gone up. And so this equation that you'll see, M1V1 equals M2V2, is based off of the idea that the moles of the solutes are equal to each other. Now, while M1V1 equals M2V2 is used often, it is a shortcut, and so I just want to make sure that you understand why you can use it, because it's not always true. And the times when it's not true is when you're looking at this and we're looking for moles of one object. So let's say that this is moles of A, and it's not equal to the moles that we're looking for in the other one, moles of B. Most often, this happens in a titration problem where you might have something like H2SO4 and sodium hydroxide getting neutralized. Because you need 2 of those sodium hydroxides to neutralize 1 of those sulfuric acids. And then your equation M1V1 equals M2V2 kind of falls apart. So I just want to clarify that because you'll notice that in my answer keys, I very rarely just write this equation. I normally just solve it for the moles because it's what you're doing anyway. So I feel like it's easier to just break it apart. But a lot of the YouTube tutorials and things like that that you see, they do it that way. And so I just want you to know why I do it my way. Both of them are fine as long as you know when you can't use it. So in this case, what we're doing is we're changing the volume of our compound, of our solution, sorry. We're taking it from being 4 liters to being 10 liters overall, or 4 milliliters to being 10 milliliters overall. So we can multiply this by our molarity. And we can find our moles. The only part is we have to make sure that we change those 4 milliliters into liters. So it's 0.1234. We have to take that 4 divided by 1,000. And so we get our number of moles here. And then we can put that over our new volume. That's going to be our 10 milliliters. If we put that in liters, that's 0.010 liters. And so we end up with the molarity of 0.0100. So I'm going to get rid of this. Of a copper sulfate. And you can kind of see that we have 3 significant figures for all of them. And so our concentration at the end is going to have 3 significant figures as well. Do you guys have any questions about that type of dilution problem? Okay. So then let's have you guys look at some of these ion concentrations. So when you look at this compound, you want to decide whether it's going to be an electrolyte or if it's going to stay together. And then if it is an electrolyte, what ions is it going to break down into? So once we have that, then we should be able to update the concentrations of those ions. And you can assume for these that if they are going to disassociate, then you can assume that they're a strong electrolyte, so they're going to completely disassociate. So let's start with this first one here. So we have ammonium sulfate. And so what's one of the ions that forms from ammonium sulfate?
Ammonium.
Ammonium. So that's NH4 plus. And what kind of ion is NH4 plus?
Cation.
It's a cation. And what other kind of ion is it?
Polyatomic.
It's a polyatomic ion, right? And so that's how we know that it sticks together. And so what's our second ion that we're going to form there?
SO4 minus
SO4,
2.
2 minus, right? And so now looking at this, when one of these molecules or I guess formula units dissolves inside of water, do we get one of them out for each? or how many of these NH4s do we get out?
Two of them.
We get 2 of them. So if we look at this, the number of ions, 2, times the concentration of that formula unit, or basically of that solution, would tell us the molarity of our ion that we would have present inside that solution. Because there's 2 of them, then there's got to be twice as much. On this other one, it only makes 1. So we almost have we do have twice as much of that NH4 plus compared to that sulfate inside of our solution. So go ahead and work through those next ones. For question number 4, it wasn't so much that you had to see that they were equal, but you had to understand that when we add in water, the part that's not going to change is this copper sulfate. So when it's asking us for the molarity in the diluted solution, it's asking us moles of copper sulfate over the volume of our solution. And we should see that this would be equal to the moles in that first solution. So we could have used M1V1 equals M2V2 because those 2 values were the same. Or you can just use it that you need to go from to find the moles of the copper sulfate. We can go backwards and we can see that moles of copper sulfate was equal to moles of copper sulfate in the first one, which was equal to the volume times its molarity. So for B, what ions do you guys see for B?
H plus and NO3 minus.
We should have an H plus and NO3 minus. What kind of compound was B?
Acid.
An acid. Very good. This is an acid. This is nitric acid. So that was that really concentrated one you guys used when we did the copper cycle of reactions. And so for our molarities, do we need to adjust any of them? Or are they going to be equal to the concentration from B? When we're thinking about the concentrations of the ions, do we need to adjust any, like kind of what we do with ammonium? Or are they going to be the same as this concentration?
They're going to be the same.
They're going to be the same because each of those HNO3s made 1 of each of those ions. Now for C, what ions do you guys have present for C?
We're talking about C, right?
C. Mm-hmm.
So 2 Na plus and CO3 minus 2.
Right. And so for some reason, people commonly make the mistake where they just like to put that sodium all together. Right? And then they put the plus there. But here we have to remember that sodium, it's really an individual ion, and each one of those ions has a +1. So we need to multiply that concentration by 2. To get its concentration, and then our carbonate can stay the same. Now, do you guys have any questions about that part? So when we talk about the ions, just make sure that you leave it as Na plus. It shouldn't be Na2 plus. That's not correct, right? And it's not Na2 plus. That would also not be correct. Right? Na2 plus is actually would be a different kind of ion. And normally our metals don't do that. The only one that does is mercury, but you don't have to worry about that part for our class. So we can move on to our last one. We have potassium and chlorate. So how we're getting those numbers is that we're looking at this compound and we're looking at how it breaks down. So when we dissolve that and we disassociate it, that sodium carbonate is turning into 2 sodium plus ions and 1 carbonate ion. So it's not that this is 2.0123, it's that this is 2 times 0.123. And that's because this concentration here is telling us how many of those sodium carbonates are dissolving. So we know 0.123 of them are dissolving. And we know that every time one dissolves, we get 2 sodiums out. So we should be twice as concentrated, which is where the 2 times comes from, compared to it as a unit together. And so that's how we get the 0.0 or the 0.246. When they're equal to each other, like what we have with the carbonate, because when 1 sodium carbonate dissolves, we get 1 CO3 2 minus, then those concentrations stay the same, and we get 0.123 molarity. And so we're just looking at those ratios between them. Very good. So the second part of solutions is when we start to apply them kind of like what we would do with stoichiometry. So now instead of going just from grams to moles, moles to moles, and moles to grams, we can use these concentration units to be mixed in there as well. And so in this process, I've given you the reaction here. So you don't even have to know the reaction. I've given it to you. Is this reaction balanced? What do you guys think? Does it look like we're balanced?
Yes.
Yeah.
So we are balanced here. And so then the next part that we need to go through is now we can use this to kind of answer our question, right? So even when I provide you with reaction, it's always good practice to make sure that it's balanced so that way you guys can use it for its conversion. And so our question is asking us what volume of our nitric acid in milliliters is required to react completely with 1.30 grams of barium hydroxide. So we're looking for nitric acid and we're looking for that in milliliters. Now, if we want to go from barium hydroxide into nitric acid, what unit do both of them need to be in for us to make that comparison?
In mole.
Moles. So both of those cases, we have to go from moles to moles. Anytime you change from one thing to the other is we're going to go from moles to moles. So how can we take that barium hydroxide and turn it into moles?
Molar mass.
Molar mass, very good. And if we have the moles of barium hydroxide, how do we turn that over into moles of nitric acid?
From the equation.
From the equation. So if we have 1 mole of barium hydroxide, how many moles of nitric acid would that be?
2.
2. All right, so we're close to there. Now, from our moles of our nitric acid, how can we get that into a volume? How can we go from moles of nitric acid into a volume of it?
The molarity.
The molarity. So we can use the molarity, 1 liter of our HNO3 solution is 0.125 moles of HNO3. And then what's our last step that we need to do? After we go through all of that, what's the last conversion that we have to do in order to get into milliliters?
Multiply by 1,000.
Multiply by 1,000. Very good. So I'll let you guys kind of start to fill those in. We can see how we did for our first stoichiometry problem in quite a while. All right, we got our first one in by Claire. We have 121 milliliters. We see how everyone else does. Oh, Ashley's got 121 as well. 121.4. Right, so it looks like we're falling in the right place. Now, how many significant figures should our answer have for this one?
Would it be 3?
Should be 3. Right, so that's why we should end up at 121 instead of 121.4. Very good. All right, very good, you guys. So at 121. So this next one, right? So this is the 121. You guys are right for that one for this milliliters. What I want you guys to do is I'm going to let you guys start on number 7 by yourselves. So I'm not going to write out the pathway for you to kind of give you guys a chance to really work through that. And so I'm going to give you guys about 5 minutes. So at 11:50, we'll come back and we'll start working through that problem. So if you're already finished with number 6, then move on to number 7. You guys can get started with that. If you have questions on number 6, we can do that as well. Or if you get stuck on question 7, then message me and I will send you back some guided advice just to you. But we're going to give this kind of like a 5 minutes. So that way you guys can kind of move this along. I want you guys to practice setting up your own pathway.
So number 7 is very similar to 6, right? It's the same, right?
So I'll give you guys about another minute and then we'll talk about it as well. Have a good one, Brian. All right, so it looks like we got 2 in for 193 milliliters. And so the layout for this one ends up being very similar to the layout of the one before. We're starting off with the grams of our product that we want to dissolve, right? This is the silver bromide. And so we need to get that over into moles, so we use its molar mass. And then we use the balanced equation in order to change it from the moles of silver to the moles of sodium thiosulfate. Once we have that, we're going to divide by our molarity in order for us to get the volume. And then we can use that to find our volume of solution we need. And so you guys are right. The volume that we need is 193 milliliters. The things to check is your molarity, or not your molarity, your molar mass for your silver bromide should be 187.77. Make sure that you use a 2-to-1 ratio for your moles to moles. And then make sure that you turn it into milliliters at the end. If you got 0.193, that's because you're giving the answer in liters and not milliliters. Does anyone have any questions on that part? Okay, so we're going to look at number 8 as our last problem. Now, number 8 is a titration problem, but a titration problem and a stoichiometry problem are very similar. Now, a titration problem, we should feel comfortable with coming up with these equations on our own because we should understand our neutralization reaction. But a titration problem is really us doing stoichiometry with 2 solutions. We can still use grams in this case, but we could have also given to you in volumes as well. In either case, what we want to do is we want to end back up in our mole to mole ratio. So for this one, we're starting off with our grams of sodium hydroxide, and we want to figure out a volume of HCl that we need. So if we start with grams of sodium hydroxide, what do we need to do to that as our first step?
Molar mass.
Molar mass. When in doubt, turn everything into moles. If you're not sure, one of the first things that you might need to do is turn it into moles. All right, now we have it in moles. How do we move it to our HCl? What's our next step? If we're going to have that sodium hydroxide in moles, how do we move that to our HCl?
From the equation, the molar ratio.
And so what's the ratio for our HCl to our sodium hydroxide?
1:1.
1-to-1.
1-to-1, very good. And so once we have that in moles, how are we going to get that into a volume for our HCl?
Molarity.
Are we going to multiply by the molarity or divide?
We are going to divide by the molarity.
Divide by our molarity. And then we just need to change it into our milliliters. So I'll let you guys get through that one. So this is a lot of what your next quiz is going to be on, right? I put up the expectations for chapter 12 in the, I'm going to look for the page, and once I find it, then I'll be able to tell you what exact page it's on. So the expectation for this quiz, it's put into the final exam one, but I'm going to go ahead and I'll relink it to our page for today. And so we have the expectations in there, and then I'll show you what those are, and we'll talk about that. And you guys are right that our last answer should be 40.9 milliliters. Okay. So very good. I'm going to show you guys what's going on for chapter 12, what the expectations are, and then what I want to walk you guys through where you guys can find some more practice ones for those. That way, at this weekend, as you guys practice, you'll be able to move through those as well. What we covered today is the vast majority of you guys' quiz, but there is a little bit extra. So the last section that you have that's available is your colligative properties. Right? And so we've kind of covered this whole first part. We've covered your solutions, the different types of concentration units, things like that. What we didn't cover is this colligative properties with our boiling point elevation and our freezing point depression. We also didn't talk about like dissolves like, right? And so both of those things are available. So that might be if I was to give you several different compounds and ask you whether they would dissolve in water or not, you would have to tell me whether or not that would happen. So if I told you, does CH4 dissolve in water, what would you guys say?
No.
Why?
Is this a non-electrolyte?
So it's not that it's a non-electrolyte that is the problem, right? But CH4 is non-polar.
Oh, that's it.
Right? So when we're looking at whether something dissolves, we're looking to see if they're soluble in each other, and so it's like dissolves like. Right?
Okay.
Now, if I told you that was CH3Cl, right? CH3Cl is now a polar molecule, and then we expect that it should dissolve in water because it's a polar substance in the polar solvent. And so that's kind of what we're looking at for the like dissolves like type of problems.
All right.
Okay. Boiling point elevation and freezing point depression. To do those, we have to use our molalities. And so if you guys have your solutions practice problems page, we start to get into this part a little bit more in the advanced one. Right? So these first two problems are what I would recommend starting with when you guys are ready to do your freezing point depressions and your boiling point elevations. Now there's already a key up for them as well. So if you get stuck, then there's something to help you with those. But that's a smaller part of the chapter. The colligative properties is not the main focus. The main focus is being able to do things like molarities, molalities, concentration changes or dilution changes, things like that, using it in stoichiometry. Colligative properties isn't a part of it, but it's a smaller part of it. Does that kind of answer your guys' question about what to expect for your quiz on Monday, or on Tuesday?
Yeah.
Okay. Now, the reason why we have two finals is that your first final is exam number 4. I had tried to remove exam number 4, but to be honest, because of how people did on exam number 1 and exam number 2, some people needed that extra exam in order to bump up those scores, right? Otherwise, your final exam basically would have been worth like almost 30% of your grade, and the other 3 exams would have been closer to 15, and so it was kind of rough for some people that did poorly on the first one. The second part is that instead of having one final exam that will be really long, like closer to the 3 hours, we're going to have 2 smaller exams, right? So your first exam, the one that happens on Tuesday, that one's all multiple choice. It's going to take a little bit under 2 hours to do. It's a slightly different style. It's a lot of questions, but the questions are a little bit simpler, right? Because it's all multiple choice. And so you just have to kind of go through those